Hello and welcome back to the Core Learning channel. Today we're going to be looking at redshift. So first of all, we're going to consider how light is created. And to do this, we're going to think about atoms and electrons. So the basic composition of an atom is that we take a nucleus and then we have some energy levels. So in this particular case, there are two energy levels. Depending on what element we're looking at, it will have a varying number of energy levels. For instance, hydrogen has one energy level, and then as we have more protons and more electrons, the number of energy levels will increase. And then obviously in these energy levels, we have electrons. So we're looking at how light is created. So this is essentially the process that happens. You have this photon. So a photon is a little packet of energy, essentially. And it's what we would consider to be light. So light is made of photons. It is one unit of light energy. So it comes hurtling in towards the electron. The electron absorbs the energy of the photon and it jumps to a higher energy level. It then because it is unstable, it then falls back to its original state. And in doing so, it releases a photon. So this is a continual process of absorption and emission of photons. So this is how this process comes about. So let's actually just take a closer look at what's going on here. So we have this electron sitting in the first energy level, and then we have this photon. The photon hits the electron. The electron then gains this energy from the photon and moves up to the second energy level. After a while, it becomes unstable at this energy level and it drops back down. In doing this, it then releases the energy that it had before and it releases another photon. So we've just considered how a photon is released. And in this case, a photon is light. So what I want to know is, how do we interpret this? How do we see this? How do we interpret light? So let's say that you're looking at the sun, which I definitely don't recommend you doing, but you've looked at the sun, and inside the sun, this reaction that we just discussed on the previous slide has happened, and a photon has been released that is traveling towards Earth. So a photon is an electromagnetic wave. What this means is it is traveling at the speed of light, which is 300 million meters per second. So as a wave, it is going to be oscillating towards you at this speed, which is 300 million meters per second. Once it reaches your eye, obviously then there are complex processes within your eye that are able to interpret this light. But that is essentially how light travels from an object to reaching your eye. So at the moment the light is technically released from the sun, you wouldn't see it, but you see it once it has traveled to your eye. Now obviously because it travels so fast, in most instances when light is released you see it instantly, but particularly for distant objects in the universe such as stars in distant galaxies, the light you're actually seeing takes a while to travel to your eye. And even in the case of the sun, the light actually takes about 8 minutes from it being released from the sun to you actually being able to see it. So the last thing I kind of want to talk about before we directly address redshift itself is the electromagnetic spectrum. And what this is a range of frequencies of electromagnetic radiation. And what I mean by radiation is simply essentially energy or light. And what it looks at is the relationship between wavelength and the energy of the waves. So what you can kind of see here on the right hand side is that the larger the wavelength, the smaller the amount of energy of the wave, and the smaller the wavelength, the larger amount of energy of the wave. So this has an inversely proportional relationship. So as one increases, the other decreases, and vice versa, obviously. So radio waves have the highest wavelength but the lowest energy, and gamma rays have the lowest wavelength but the highest energy. And what's quite important to note here, as you can see on this diagram, is that when we expand out the visible light, we have red light towards the higher wavelength, lower energy side, and we have blue/violet towards the lower wavelength, higher energy side. And I'll discuss that briefly on the next slide. So carrying on from what I was saying on the previous slide, and I think this diagram actually illustrates this quite nicely, we can see that the red visible light is towards the longer wavelength side of the spectrum, and the blue/violet side of the visible light spectrum is towards the lower wavelength side of the electromagnetic spectrum. So this is kind of where the term redshift or blue shift is derived from. Hopefully you might be able to already tell, but if not, when we talk about redshifting a wave, what this means is a wave that is increasing in wavelength. And when we talk about blue shifting, this is talking about a wave that is decreasing in length. So what this would correspond to for redshifting is a wave that's being perhaps stretched, and in the case of blue shifting, this is a wave that's being compressed. And I've kind of just put this on here to highlight that we can see that redshift is when we move towards the radio wave end of the spectrum, and blue shift is when we move towards the gamma ray side of the spectrum. But it's basically just a movement in one direction. So it's about moving towards higher wavelengths in the case of redshift, or moving towards lower wavelengths in the case of blue shift. So the key takeaway from this is that the redshift is when light/electromagnetic waves are being stretched, and blue shift is when they are being compressed. And you can actually think of this in terms of the Doppler effect. And this is really an example of the Doppler effect. Now, most of the examples when you talk about the Doppler effect will be in terms of sound waves. So we can actually use quite a good analogy here using sound waves. Consider you're standing on the street and there's a police car in the distance. It's got a siren on and it's coming towards you. So the sound of the source of the sound, the police car, as it's emitting this noise, it's emitting these sound waves, is driving towards you. So when these sound waves are reaching you, as it gets closer and closer, the sound waves are becoming more and more compressed. And what this results in is a much higher pitch. And, you know, if you're ever in this situation, actually take a moment to listen, and you'll notice as the police car is coming towards you, or an ambulance or fire engine or whatever it is, the pitch becomes higher and higher and higher. So it gets to you, and then it starts going off past you. And now the source of the sound is moving away. So what happens is the sound waves are becoming stretched, and it becomes a really the tone becomes lower and lower, becomes a much lower pitch, and this is completely analogous to what we're talking about here. For example, if we now take this back to visible light, the example would be that we have some distant object moving towards us that's emitting light, and as it moves towards us, obviously the visible light is becoming compressed, so this would be blue shifted. This means as it got closer and closer, to an extent it would appear more blue. Then as it moved past, we would expect the light to become stretched as the source of the light is moving away. And in this case, it would begin to appear more red. So if you're ever sort of struggling to remember to actually think about this, it's often useful, for me anyway, it was quite useful to think about the Doppler effect, as it draws sort of a really nice analogy between this stretching of waves and comparing it between light and sound. So we've looked at what redshift is, but why is it important? Well, quite simply, comparing the spectrum of different spectral objects, so this includes distant stars, galaxies or quasars, to the spectrum of the sun, it is found that the wavelength of the light coming from these distant objects is actually larger. Well, the reason it's larger is because it's been redshifted, and it's been redshifted because clearly the waves of the light are being stretched, which would suggest that the object is moving away from us. And what this means is that the universe must be expanding. So that is one of the real important findings using redshift, is that is evidence that the universe is expanding. So thanks for watching this video. Hopefully you found it helpful. If you did, please like and subscribe. If you have any questions, leave it in the comments and I'll try to get back to you as soon as possible. Thanks, guys.